Welcome to this NPTEL lectures on robotics, basic and advanced concepts. Okay. In the last lecture, we had looked at control of a single link using linear control schemes. In this lecture, we'll look at control of a multi-link serial manipulator, again using linear control schemes. Okay. So in the case of a multi-link serial manipulator, we have n joint variables, which will be denoted by Q. We have the desired joint motion QD available from motion planning. We also assume that QD dot and QD double dot are also available. Okay, so when we did this motion planning using cubic trajectory, we could take the derivative of the cubic polynomial and obtain QD dot. We can take again derivative and obtain QD double dot. So these are available. So in the lecture, we'll look at PD control of a multi-link manipulator. The actual implementation is PID. So as discussed, we also sometimes add, or we not sometimes, we always add a I part, which will get rid of the steady state errors. But as far as analysis is concerned, we stick to PD because it is simpler to do. Okay, I increases the order of the system. So we will look at some simulation and experimental results with a 2R manipulator. So PD control of multi-link serial manipulators, we extend this whole notion of continuous time control of a single manipulator. Okay, single link manipulator. So what do we have? We have the voltage which is applied is proportional to the second derivative of QD, which is, so this is like acceleration, kV into E dot of t, Kp into E of t. Okay, so E of t is QD minus Q. This is implemented actually with the integral term, but as I mentioned, we will not consider the integral term in this analysis. Other important thing is we actually use torque acting at the joint instead of the voltage in the analysis. Okay, so is this very serious? No. Why? Because the torque is related to the current. Okay, Tm is Kt times Ia. Then this current is related to the voltage applied. There is a back EMF. Nevertheless, we can think of that voltage and torque are related. Okay, we can also obtain this voltage from the motor characteristics. Okay, we get the torque speed curves, and that is for every voltage there is a certain torque at a different speed. Okay, so as far as analysis is concerned, for the sake of simplicity, we will assume that we are inputting torque, not voltage. So what is the control law which we will use? That it is tau of t, which is QD double dot plus kV into E dot of t plus Kp into E of t. Okay, actually, strictly speaking, it should have been voltage, which is related to motor torque in some manner, but we are going to assume that it is torque that you are applying. And again, E of t is the error between what is desired and what is measured. And we will see what a linear control law does when you are applying it to a nonlinear system. Why? Because a multi-link robot is known to be a nonlinear system. Remember, the equations of motion of a multi-link serial manipulator contain all kinds of nonlinearities. You know, theta 1 dot, theta 2 dot in the case of 2R, then sine and cosine of the angles. Quite a few nonlinear terms were there. So how does it look like? The PT control of a multi-link serial manipulator using a linear control scheme looks like this. So I have this robot, the input is torque. The output, we are going to measure Q, which is the rotation at the joints, and Q dot, which is the velocity of at the joints. Then we do Q D minus Q. So this is the error multiplied by Kp, and then QD dot minus Q dot measured multiplied by Kb, and to that we add this QD double dot. Okay. So each joint or motor is independently controlled. Okay, and all the quantities qd, q, and tau are n by 1 vectors. So if we have an n degree of freedom serial robot, these are n by 1 vectors. And kp and kv are n by n positive definite gain matrices. Okay, it could be diagonal, which is easier to analyze. If it is non-diagonal, then there is some coupling. Nevertheless, they are positive definite gain matrices. The gains must be positive. So the multi-link manipulator is a nonlinear system. We have looked at the equations of motion and they are nonlinear. And as a result, what will happen is you will not get uniform damping and settling time everywhere in the workspace. Okay, so the performance of the robot in terms of damping, settling time, and so on will be different at different places, because basically the manipulator system is different at different places. Okay, PD control still works because basically we run these robots at slow speed most of the time. Okay, and also because we have large gear ratios. Remember, in one of the examples earlier, when we were modeling the single link, we had a large gear ratio, and due to the large gear ratio, the disturbance torque TD, which is basically the torque acting from further away links onto the link which we are interested, is reduced by the gear ratio. Okay, so that is the reason this PD control often works. And there are still many manipulators, which are serial manipulators, which are manufactured, which use PD control laws, linear control laws. The linear control is most of the time implemented using one or more microprocessors. Okay, and earlier in the original days of robotics, there were two main kinds of architecture which were used. One is what is called as a joint parallel architecture. So each joint is controlled by a microprocessor. An additional master or a coordinating processor is used for graphic user interface, data logging, and various other things. There was for a short while something called as a functional parallel architecture, where each group of functions and tasks were handled by one processor. So for example, the inverse kinematics was done by one processor, motion planning was done by one processor, and so on. Most of the time, this joint parallel or independent control of each joint is the common way of controlling a serial, multi-link serial robot. The original Puma robot, for example, had something called as a 6503 microprocessor at each joint. Most of you would not have heard of what is a 6503 microprocessor, but 50 years back, this was well known. The master computer or the coordinating microprocessor was a DEC LSI 11. This is also does not exist anymore. Okay. Theta D was available every 28 milliseconds. Okay, so we compute or do this motion planning, and every 28 milliseconds a new theta D was available. And the sampling time for the joint processor was 0.875 microseconds. Okay, remember we have to calculate the error, we have to sample the input and sample the output. That TS is 0.875 milliseconds. The modern solution is basically a controller based on industrial PCs to control several joints. Okay, so we might have a card which controls all the joints. We might have another card which does maybe all the GUIs, okay, or controls all the other peripheral devices. So let's continue with the PD control of a 2R manipulator. The equations of motion of a 2R manipulator were derived earlier, okay, but I am repeating them again. So tau 1 and tau 2 is given by some mass matrix into theta 1 double dot, theta 2 double dot, some centripetal Coriolis term, and a gravity term. Okay, so this mass matrix is 2 by 2. It is positive definite, symmetric, and so on. The desired joint trajectories are specified, nice cubic smooth trajectories. And what we are going to use is a linear control, which is tau I of t is theta double dot of t plus kv ei dot plus kp ei, where ei is nothing but theta id minus theta. Okay, so on the left hand side, this tau 1 and tau 2 will be substituted by this. So let's take an example. So we have a 2R manipulator. So basically there are two joints, 1 and 2. So at O1 and O2, first joint rotates at theta 1, second joint rotates at theta 2, relative rotation. Tau 1 is the torque which is acting at the first joint. Tau 2 is the torque which is acting at the second joint. So we have mass, length of the first link, location of the CG of the first link, R1, I1, which is the Z component of the inertia of the first link. Likewise, M2, L2, R2, and I2, which is of the second link. Okay, we have to choose some parameters, and remember, in the case of dynamics, we have chosen L1 and L2 as 1 meter. We are sticking to those same lengths, locations of the CG, and the masses and inertia. Okay, so M1 was 12.456 kg, I1 was 1.042 kg meter square, and so on. Okay, we will also assume that there is a payload at the end, at this x and y, and the trajectory is that we want to go from x comma yi to x comma yf, okay, and then come back, and the gravity is acting this way down along the y-axis. So the tip moves from 0, 0.55 meters to 0, 1.45 meters. It lies completely in the workspace, and back to 0.55 meters. And we will consider two cases in the simulation. One, which is fast. So the total time is 1 second. So it goes up in 1 second, comes down in 1 second. Okay, it's pretty fast. So it is like of the order of 1 meter per second speed. And another trajectory which is very slow, which is 1 meter per minute, of the order of 1 meter per minute. Okay, so what is the desired trajectory? The x should be 0, and we will fit a cubic, nice smooth cubic trajectory in the y direction. So it goes from 0.55 to 1.5 in 1.45 in a cubic profile in 1 second, and again it comes down back to 0.55 as in a nice smooth cubic profile in between 1 and 2 seconds. Okay, now for these trajectories we can find the desired theta 1 and theta 2 by doing inverse kinematics. Okay, so we obtain the desired theta d using inverse kinematics, and then we perform simulations for PD control scheme. Okay, the gain values kpi and kvi are chosen such that omega 1 and omega 2 are 85 and 75 arbitrarily. Okay, these are the two natural frequencies. Remember, for a second order system, we can describe everything by natural frequency and damping. And the psi is chosen 2.0. We basically want overdamped. Okay, we don't want oscillations as it goes to the top. So we can perform these simulations. We go back to the equations of motion, solve the equations of motion, integrate the equations of motion, because we can see everything is known now. So in this, theta id is known. This is theta d minus theta t. So theta d is known, theta d dot is known, and then we can rearrange this equation in state space form. The output of the integration will be theta, which we can subtract, and then basically we can do everything, and we can find theta as a function of time. Okay, for the chosen kp kv, for the chosen i1, i2, m2, l1, all the parameters. Okay, the gain values were chosen arbitrarily like this. We could have chosen some other gain values also. So let's plot theta 1 and theta 2 for the fast motion. So as you can see, the error in theta 1 goes up, okay, as you are going up. So up till 1 second, it is going up, and from 1 to 2 seconds, it is coming down. So you can see that the error is of the slightly less than 0.03 radians. Okay, the y-axis is in radians. So that's quite a bit. 1 radian is 57 degrees approximately. So 0.03 is like almost how much? 1.5 degrees. Okay. The error in x and y can also be plotted. What do we want? The desired x should be always 0. It should just go vertically up and down. However, because of this coupling and because of this is actually a control, we will never get the exactly desired trajectory. So we can see that there's an error in x and there is also an error in y. And this is of the order of 2 centimeters, between 2 and 2.5 centimeters in x, and between 1 and 1.5 centimeters in y. And what is the plot of torque? Because we can, once we have solved, we can plot the torque. The torque is of the order of 200 and maximum torque is of the order of 225 Newton meters in tau 1. And the second torque will be less because it is expected. We expect that the second motor to provide less torque. It's seeing less inertia. It's of the order of 150 Newton meter. Okay. So the important thing are these nature of these plots. Whereas if you look at the slow motion, which was you go up in 1 minute and come down in another 1 minute as opposed to 1 second and 1 second, you can see that the error is smaller. Okay, previously the error was between 0.02 and 0.03 radians. The error in x was between around 0.025. Okay, so now the error is less than 0.02. Okay, the error in x is less than 0.15, so 1.5 centimeters. Okay, the torques along the trajectory is also smaller. So instead of previously we were reaching about 225 or 230 Newton meters, now we can do with less than 150 Newton meters. Okay. So what are we seeing? That the maximum error in the joint variables are larger in case of fast motion. They are approximately 0.03 radians in fast versus 0.02 in slow motion. Okay, approximately 0.023 meters in the x, whereas 0.016 in the slow motion. And why is this? Because in the fast motion we have nonlinear inertia, centripetal, Coriolis terms which are much larger. Okay, so the nonlinear terms are significantly larger when it is moving faster. We are using a linear controller. Okay, so we are trying to control a nonlinear system using a linear controller. Okay, so if the nonlinearity is more, the performance will be worse. That is expected. And in a fast motion, the Coriolis term, the centripetal term, and the inertia term are much larger than if it is moving slowly. So hence, we expect in the fast motion the performance to be worse than when it is moving slowly. So the linear PD control is less effective for fast motion as expected. Moreover, the maximum torque at the joint is larger. Okay, this is also because we are seeing larger Coriolis and centripetal and inertia terms. Okay, so it's approximately 225 Newton meters versus 145 Newton meters. So the larger torque in fast motion is due to nonlinear terms in the equations of motion as expected. Okay. Also, the curves are much smoother in slow motion. Till now, we have looked at simulation results of multi-link robots. In the next few slides, I will show you experimental results on a planar 2R robot, and I will show you what are the experimental results for a PD control scheme. Remember, we have looked at PD control scheme in which there is a proportional gain and a derivative gain. A little bit of description about the experimental setup. So this is a 2 degree of freedom planar robot. It consists of 2 rotary joints. The link lengths are 150 mm each. The actuator details there are two motors, motor 1 and motor 2. As I will show you later, these are two BEM motors made by Kondo. Okay, the maximum torque which these motors can apply is 7.6 Newton meter. The dimension is quite small. It is 51 mm into 32 mm into 39.5 mm. The weight is about 105 grams. There is a standby current of 68 milliamperes. There is a stall current of 5.4 amperes, and there is a reduction ratio. These motors are controlled by a Texas Instrument microcontroller, which is TM4C123GH6PM. We will use programming language C to control the motion of these motors. And the control scheme that we will use is PD control of motor velocity. Okay, this work was done by Pramod and Aditya at the Robert Bosch Center for Cyber Physical Systems. So here are some of the components. So the servo motor is Kondo B3M SC1170A. Anybody is interested later to purchase this or get hold of these motors. Okay, these are reasonably good servo motors, little bit expensive, but nevertheless these are good servo motors. Okay, there are some connectors which are called hub type A for XH connectors. Then there are some cables for these XH connections. We need a battery. So this is an 11-volt lithium-ion battery. Then we need some kind of a USB to serial conversion adapter. Then we have this actual microcontroller, which is made by Texas Instrument, TIVA-C. Okay, then you need all these cables and a laptop. So with these components and of course the links, okay, we can do these experiments. So the way it is connected is from the laptop, you connect using a USB cable to this microcontroller. Then using this RS485 USB to serial, which also requires a power connection, which is this microcontroller to this RS485 USB serial. This is the electronics part, and you can connect to this B3M motors. So we are going to connect to two such motors. Okay. So for PT control, we need to give a desired motor's joint position. Okay. So the desired motor joint position for motor 1 and motor 2 are these blue sinusoidal lines. Okay. So we want the first joint, which is the first motor, to follow this blue trajectory as a function of time. We see that if you use a proportional gain of 2 and a derivative gain of 1 for these two motors, the achieved joint trajectory is this orange line. Okay, so clearly it is not doing a good job with these controller gains. Okay, KP_2 and KD_1. So let's increase the controller gain. So we have done several trial and errors, and eventually we obtain a proportional gain of 25 with a derivative gain of 10. And in that case, you can see the blue, which was the desired trajectory, and orange, which is the actual achieved trajectory by the motor, are more or less matching. Okay, so what have we done? We have taken this motor and planar to our robot. We have given a desired joint trajectory for both joint 1 and joint 2, and then we have played around with the proportional and derivative gains till we achieve some reasonable matching between the desired and the measured trajectory. This measured trajectory is from a measurement device on the motor itself. Okay, so the left hand side shows the setup and also the right hand side. This is the 2R robot, and we start with a proportional gain of 2 and a derivative gain of 1. Okay, this simulation here shows up the performance of this planar robot, 2R robot, when the proportional gain is 25 and the derivative gain is 10. Okay, so you can see that there is a scale which is drawn, which gives you an idea of how much is the error. So as you can see, when the gains are small or when the gains are low, the motion is very, very uneven. Okay, it is not really tracking this desired trajectory along the y-axis. Okay, whereas if you have higher gains, you can see that the motion is much more smoother and it is tracking the trajectory reasonably well. Okay, so we can do similar experiments with other systems, and the moral of the story is that we need to play around with the controller gains till we achieve a desired trajectory. Okay, thank you.